All right, hi everybody. So today we're going to talk about buffer solutions. So first off, what is a buffer solution? It is a solution that contains a weak acid or base and a salt containing the conjugate ion of the acid or base. So it's a mixture of a weak substance, either acid or base, and then a salt that contains the conjugate acid or base ion. So buffers resist changes to pH. Since they have both an acid and its conjugate base, or a base and its conjugate acid, they are able to react with any substance that it comes in contact with and resist those changes in pH. So some really good examples and common examples that you guys are going to see of buffers. Things like ammonia, which is a weak base, and ammonium chloride. Okay, it doesn't have to be ammonium chloride. It could be any salt containing the ammonium ion. But you see the weak base and its conjugate ion here. Another one that's really common is acetic acid, which is a weak acid, and then maybe the sodium salt, so sodium acetate. So there's the conjugate ion, okay? So some things that would not be considered buffer systems. If I have a strong acid like HCl and its salt, that's not it, okay? If I have something like hydrochloric acid, which again is strong, and sodium hydroxide, that's not necessarily going to be a buffer solution, okay? They probably react and form water, and then one of them would be in excess. So how do buffers resist changes in pH? Well, listen, if we add an acid, right, if we add the hydrogen ion, then that acid is going to react with the base. So for example, that first buffer system we had was ammonia and ammonium chloride. Well, this is the base, and this is the conjugate acid of that base. If I add hydrogen, that acid is going to react with the base in this system. So if I add hydrogen, it's going to react with NH3, and it's going to form that ammonium ion. Okay, so the ammonia is willing to react with the hydrogen to form ammonia. The pH is not going to change because that hydrogen is not free floating in the water. It has become part of the ammonium ion. If sodium hydroxide were added, then the acidic part of that solution would react with the base. So base has to react with acid. Well, in that system, the ammonium ion, NH4 positive, was the conjugate acid. So that's the acid part. If we add that base, the hydroxide is going to react with it, and what we're going to end up with is water and ammonia. So the water and the ammonia are products. We don't have any hydrogen or hydroxide free floating in the water. So again, it's going to take this hydroxide, which would change the pH, and react it to form two things that are not necessarily going to change the pH too much. And again, buffers have both acid and base ions. So they're able to neutralize both. Okay. Now to calculate the pH of a buffer system, we use a modified version of the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation, and we're in chapter 15 of the book right now, it has to do with pH and pKa, but instead we're going to use a modified version that takes that negative log out of the equation. And so the form of the equation that we're going to use is the hydrogen ion concentration is equal to Ka of the acid multiplied by the acid over base. I always remember it as A over B. It's in alphabetical order, right? So acid over base. So H plus is equal to Ka acid over base. Even if we're given a Kb, even if we're given hydroxide ion concentrations, this is the equation. So we have to turn those into hydrogen and Ka in order to use this equation. So here's an example problem that we have. It says to calculate the pH of a buffer solution made with 500 milliliters of 0.35 molar ammonia and 500 milliliters of 0.55 molar ammonium chloride. And then a Kb value is given to us. So already I know that this is a buffer system. I have the base, a weak base, and the salt containing its conjugate ion. Okay. So what we have to do is determine first what part is the acid and what part is the base. In this particular buffer system, since NH4 has one more hydrogen than NH3, then according to those Bronsted-Lowry definitions we learned, the acid is that NH4 ion and the base is the NH3 ion. Now what we need to do is we need to calculate millimoles of each, okay? And we have to make sure that we're using millimoles here, not molarity, because as we add those solutions together, their molarities change. So we're just going to use millimoles instead. Now you can use the triangle, right? Moles on top, molarity, and it's going to be milliliters on the bottom, so that we get millimoles. Okay? I don't know if you guys can see that, but this is millimoles on top, molarity, and milliliters on the bottom. We were given the molarity and volume of each. So for the NH3, we have 0.35 molarity. We're going to multiply that by the amount in milliliters, 500 milliliters. And so, hold on just a second, let me go grab a calculator. That's going to end up being 175 millimoles. Okay? All right, so for the NH4, do kind of the same thing. 0.55 was the molarity. I'm going to multiply that by the volume, which again was 500. And I get 275. Okay, so I have my amount of acid, right? And I have my amount of base. The ammonia was the base, the ammonium ion was the acid. Now in the equation, like I was saying, we must use Ka. So remember that Kw is the product of Ka multiplied by Kb. If I rearrange that, Kw divided by Kb will give me Ka. So if I take Kw, which has a known value of 1.0 times 10 to the negative 14th, and divide that by the Kb I was given, 1.8 times 10 to the negative 5th, then we will get Ka. And I think I've done this a few times. I think it's going to be like 5.6 times 10 to the negative 10th, but I'm going to make sure. Yep, I was right. So it's 5.6 times 10 to the negative 10th. Okay, so that's Ka for this system. We're going to plug all of that in to the modified Henderson-Hasselbalch equation, which will give us H+. Then all we have to do is negative log that to get the pH. Okay, so pretty simple. So H+ concentration is equal to Ka, which we said was 5.6 times 10 to the negative 10th, multiplied by acid over base. So again, the ammonium concentration, the ammonium millimoles was the acid, so it's going to be 275, over 175. 275 divided by 175. Okay, and I got 8.7 times 10 to the negative 10th. So then if I negative log that number, I get a pH of 9.06. And there's the answer, okay? So again, you just use what we know about molarity to calculate millimoles of each thing. Make sure you know which one is the acid, which one is the base. The acid should always have one more hydrogen. Plug it into that modified Henderson-Hasselbalch equation, and then solve. Now, since they will react with acid or base, what we can do is we can figure out how the pH changes if an acid or base is added. Okay, it will change slightly. So what we do is whatever is added to that solution, let's say that we have that initial buffer solution, and then we start adding acid or base to it. We need to calculate how many millimoles or moles, depends on whether you're using milliliters or liters, right, is added. Now, if it's an acid that is being added, then what we do is we add to the acid concentration. So we add to the top of that proportion, and we subtract from the bottom because the base is going to react with it. So we're losing base and we're adding acid. For a base, it's the opposite thing. If we're adding a base to the solution, then we add to the bottom of the proportion where the base is, and we subtract from A because it's reacting with the base. Then we just recalculate that hydrogen ion concentration using the Henderson-Hasselbalch equation, okay? So here's our example problem. It says calculate the pH after 50 milliliters of 0.5 molar hydrochloric acid is added to the buffer from the previous example. Okay, so let me look back at the previous example. When I did this, I had H plus equal to 5.6 times 10 to the negative 10th, with acid over base being 275 over 175. So let me rewrite that. But since I'm adding acid, adding hydrochloric acid, right, I need to figure out how many millimoles I get from 50 milliliters of 0.5 molar hydrochloric acid. I'm going to add that to the top and subtract it from the bottom because this is an acid. So I add to the acid, I subtract from the base. So first, let me go ahead and figure out millimoles of hydrogen, right? I have 0.50 molarity, 50 milliliters. I don't need the calculator. Half of 50 is 25. So H plus is equal to 5.6 times 10 to the negative 10th multiplied by, it was 275, right? But I'm going to add 25. Divided by 175 minus 25. Which if I actually go ahead and do the math, if I add to the top and subtract from the bottom, then instead of this, I get 300 on top over 150. So I'm going to recalculate this. I'm going to take that Ka value and multiply it by the proportion 300 over 150, which actually this is 2, right? 300 divided by 150 is 2. So it's going to be 5.6 times 10 to the negative 10th multiplied by 2. And my calculator gave me 1 times 10 to the negative 9th. So that's the hydrogen ion concentration. If I negative log that, since it's 1 times 10 to the negative 9th, I already know that the pH is going to be 9. So in adding a little bit of acid, it actually did slightly change the pH, but not very much. because that buffer was able to react with it and resist that change in pH. Okay, now realize that if the acid or base completely reacts, then this is a neutralization problem with excess added. So if you run out of the top or the bottom, then it's more like a stoichiometry problem. Now you just have extra acid or base in the water. Figure out how many millimoles or moles of acid or base are in that solution. Get the molarity of the solution, and then if it's a strong acid, just negative log that. So you would work that if you run out of the top or the bottom, if when you subtract, one of them is completely used up, or you end up negative on one of those values, top or bottom, then instead you just figure out the excess. And like I said, work it like an excess a reagent problem or a limiting reagent problem like the ones we did with neutralization. Okay, so buffering capacity. I mean, we know what capacity is, right? It's the amount that something can hold or the amount that something can take. So buffering capacity is the amount of hydrogen or hydroxide that a buffer can absorb without a significant change in pH, right? So how far can we get before we run out of acid ion or base ion in the water, before we run out of that buffering system? You know, how much can we react with it until we get to that point, okay? Now, the greater the magnitude of acid and base are, so the more acid and base you have, obviously the more stuff you have in the solution to react with hydrogen or hydroxide. You also want to have a buffer. The best buffers have a ratio of acid to base equal to 1 to 1. So you want a 1 to 1 ratio. That would be a good buffer because you have equal amounts of acid and base ion that can react with any acid or base invaders, okay? So whenever we are choosing a buffer, okay, whenever we want a certain buffer, right, we want to choose a buffer that has pKa, so the negative log of the Ka value, near pH. And then we want to calculate that ratio of acid to base, okay? So we have this example problem here. If we have to set up a buffer solution, what we do is, looking at the problem, it says that a chemist needs to prepare a buffer with a pH of 4.30. So this is our desired pH. Using one of the following acids, and then the sodium salt, the conjugate ion containing salt, right? We need to calculate the ratio of acid to base necessary to get that and determine which system works best, okay? So let's think about how we could do that. We have Ka values, correct? And we have a pH, which if I use our modified Henderson-Hasselbalch equation, H plus is equal to Ka times acid over base, right? Which we could turn into a ratio. I have this pH here. I can turn that into hydrogen ion concentration by using base 10. So I'm going to do 10 to the power of negative 4.30. And I get 5.01 times 10 to the power of negative 5 for my hydrogen ion concentration. So that's what's desired, right? We have Ka values for each of these. So I could plug that in for Ka, and then I could do some algebra. I could take the hydrogen ion concentration, which is 5.01 times 10 to the negative 5th, and divide it by Ka to figure out what this proportion is, okay? So I'm going to do that with the first one. I'm going to take 5.01 times 10 to the negative 5th, and I'm going to divide that by the Ka for propanoic acid, 1.3 times 10 to the negative 5th. That'll give me acid over base. I'm going to get a number in my calculator, but I can always put that number over 1, and so that'll give me the ratio of acid to base. So for this first one, for propanoic acid, I get 3.9. And so if I put that over 1, my ratio of acid to base is 3.9 to 1. So we would need a ratio of 3.9 to 1 in order to make this particular solution work. So let me try the same thing with the benzoic acid. I'm going to take that desired hydrogen ion concentration. I'm going to divide it by the Ka for this acid, which is 6.4, sorry, times 10 to the negative fifth. And I end up with 0.78, 0.78. If I put that over 1, then my ratio of acid to base is 0.78 to 1. So that's a little bit closer to 1 to 1. If I use the next one, the hypochlorous acid, it's going to be 5.01 times 10 to the negative fifth divided by 3.5 times 10 to the negative eighth. And I end up with a really big number for this one because this 10 to the 8th is really small. Obviously my Ka is not near my H plus value. My pKa wouldn't be near the pH. The pKa of this one would be closer to 8 because the exponent is 8. Okay? So what I ended up with on this one was 1,431 to 1. So the ratio would be 1,431 to 1. So the best buffer system would be this second one, benzoic acid, because it has a Ka near my H plus concentration, and so therefore the pKa would be near pH. And this is the ratio that's closest to 1 to 1. This is more like 4 to 1. This is 1,400 to 1. This is pretty close to 1 to 1. So the benzoic acid system would be the best one to prepare the buffer with that pH. So that's how you work those problems, okay? All right. Enjoy buffers.